Okay, so let's derive this very simple and powerful learning model, which is actually called the Perceptron. Okay. And to do so, we're going to use the credit application as a guide. Okay, so imagine an applicant comes along. So we have an applicant. And what is an applicant? An applicant is X, which is, salary, debt, years in residence, I don't know, you could ask an applicant for hair color if you want, I don't know, I don't care, etc. Okay, so an applicant comes, there's a vector of attributes, a vector of features, and remember, we can represent this applicant using its features, which is a input vector x, which is in a d-dimensional space. So let's call this x1, x2, x3, x4, x5, and so on. Okay. Now, put yourself in the position of the bank and imagine, they have Malik who's sitting in a dark room, waiting for a task, and the bank says, figure out a way to approve credit. So let's figure out let's try to design a simple, reasonable way to decide whether or not to approve this applicant. Okay. And the basic idea, and it's what used to be used, is, you come up with a score. You could call it a credit score if you want. Come up with a score for this applicant. Okay, so here's the basic idea. Come up with a score. Okay, and if the score is above a threshold, say yes. So in other words, you've come up with a score, and the higher the score, the better. So if the score is above a threshold, some threshold which you also need to come up with, you'll say yes. And if it's below that threshold, you say no. Okay? It's a very simple approach to approving credit. Okay. So now Malik is sitting in the dark room. How might Malik approach the task of coming up with a score? We also have to come up with a threshold. Okay, but let's see how we would approach the task of coming up with a score. Well, Malik can say, applicant has attributes / features. So, these features have different importances. Okay, so let me give an importance level to each feature. Okay. Now, salary is very important, so I'm going to give it an importance weight of 10. Okay. This weight is 10. Okay, and years in residence is pretty important, so it's going to get a weight of 1. And hair color has absolutely no importance, so I'm going to give that a weight of 0. Okay. And now, what about debt? Debt is an interesting guy. Okay, debt is an important factor in deciding whether or not to approve credit. But the higher your debt, the less likely it is that you should get credit. And this score is such that the higher the score, the more likely you should get credit. Okay, so with debt being very important, but being sort of inversely related to score, that means that the weight of debt should be large, but its sign should be negative. It should make a negative contribution. Okay, but that's perfectly fine. I can pick a weight for debt, which is, let's say, -5. So that means it's pretty important, more important than but it has a negative effect. The higher the debt, the lower the score. Okay, so I've given a level of importance to each feature, and the reasonable thing to do, the sort of first thing I might do if I were in charge of approving credit, is to say, let's weight each feature. Let's weight the features by the corresponding weights and add. That naturally produces a number, which I can take as a score. Okay. So weight the features and add. Okay, so I'm going to get 10x1 minus 5x2 plus x3, and the hair color is x4, so plus 0 times x4, so x4, plus and so on. Okay. Now let me put this in a generic form. So this is my score. Okay? So let me put this in a generic form by not committing immediately to the weights 10, minus 5, 1, and 0, although those are the ones that I picked. Let me call this weight W1, W2, W3, W4. So it happens that this is large and negative, you know, small, 0, and so on. Okay, so if we have D features, then we're going to have D weights, okay, a weight for each feature. Okay, and this score, when I put it in this general form, becomes score equals W1 x1 plus W2 x2 plus WD xd. Okay, and now I can implement my rule. Okay, if the score is above a threshold, you say yes. If the score is below a threshold, if that same threshold, you say no. I mean, in theory, you could say I have a upper threshold. If it's above that upper threshold, I say yes. And you could, in theory, have a lower threshold. And if it's below the lower threshold, I would say no. But then what do you do in between? So if you're a credit approver, you have to say yes or no. In between, you might say, well, I'm uncertain, but you're not allowed to be. Okay. So we're in this world where you have to say yes or no. Okay. So here's my score. And if this is above a threshold, then you say yes. And if it's below a threshold, then you say no. Very simple approach to approving credit. Okay, and this is more or less how it used to be done. You come up with a credit score, okay, and you compare it to a threshold. Okay, and you know, it's a very natural approach to assigning credit. Okay, so now what I'm going to do is I'm going to take this approach to assigning credit and put it into a mathematically much more convenient form. It turns out that this is a very, you know, it's a formula that I can put in a much more compact, convenient form. So, first of all, the score, okay, is a sum. So, approve, yes, if the sum from I equals 1 to D of Wi xi is greater than threshold. And no if the sum from I equals 1 to D Wi xi is less than the threshold. You might ask, what do you do if the sum is 0? Well, we'll forget about that, you know, very unlikely case. Okay, so we'll brush that under the rug. We can take it into account. We could say, for example, greater equal to, but the mathematics becomes a little bit easier by just ignoring that 0 probability case, essentially, when, you know, the x values are real numbers. Okay, now remember I said that we can encode the yes as +1. So this is my decision is yes, but that's equivalent to say my decision is +1, and my decision is no is equivalent to say my decision is -1. Okay. And now we observe that basically what we're doing is we're comparing this to a threshold and saying +1 if it's greater, -1 if it's less. So I can combine these two into an equivalent single formula as follows. Okay. I can take the sign of this value minus that value. Okay. The sum from I equals 1 to D Wi xi minus threshold. And that simple formula is my decision. So let's see if it works. If this sum is bigger than the threshold, then inside here is positive, and so the sign of that is +1, and boom, that's my decision. If this is less than the threshold, this is negative, and the sign is -1. And the fact that I'm not considering the 0 case, so the equals here just means I don't need to define the value of sign when its argument is 0. We could say that it's +1. Okay. Let me further simplify. Let me further address the form of this function by introducing another way W0, which is going to be related to the threshold. So observe that I can write this. Okay. So introduce W0 to represent threshold. Okay? In the sense that if I tell you the threshold, it's equivalent to telling you W0. And I want to write this formula as the sign of the sum from I equals 0 to D Wi x9. Okay, so notice that here the sum is from I equals 1 to D. Here it's from I equals 0 to D. Okay. Now, the I equals 1 to D part of this is exactly what appears here. So this is, it's equal to the sum, the sign of the sum from I equals 1 to D, Wi xi, plus, okay, there's the I equals 0 term, plus W0 x0. So this will equal that whenever x0 is always set to 1. Okay, so providing that x0 is 1, and W0 then becomes the negative of the threshold. Okay, so this form and that form are basically the same, providing that x0 is 1, so x0 is 1, and the weight W0 is interpreted as the negative threshold. So whatever I said as the threshold, I take as the negative, I take the negative of that for W0. Okay. So this rule that I have implemented, okay, is compactly represented by this functional form where x0 equals 1. Okay. It's a rule. It's a rule that I came up with in a very natural way by constructing a credit score and then using that credit score against the threshold to decide plus or minus 1. The only thing I've done is mathematically simplify that rule into a single formula. Okay. So, let me erase all this and summarize. So, in a very natural way, I came up with the following credit approval rule. Credit approval rule. Okay. My decision. Okay, so let's call it, because it's my final decision. So let's call and relating to the final hypothesis, we call that G. So let's call this G sub Malik, because it was created by Malik sitting in a dark room in the bank. So G sub Malik, okay, is equal to sine of the sum from I equals 0 to D of Wi xi. That is Malik's rule. Okay. Now, what is it a function of? What is G a function of? It takes as input x. Okay. And what about the W's on this? Well, I came up with those. Remember, there were the numbers 10, 5, minus 5, 1, 0, and so on and so forth. Okay, so I came up with those numbers. Okay, so the only thing that the applicant provides is the x. Okay, and then I implement Malik's final, beautiful rule for credit approval. Okay. Let me introduce a convenient notation. So we can make this functional form even more convenient by introducing a convenient notation. Namely, remember that the applicant x is equal to a vector of its attributes, x1, x2, up to x sub d. Okay. And now we have this, x sub 0. So x sub 0, we have this x sub 0, which is equal to 1 in this formula. Okay. And we have d plus 1 weights. Okay, so W is equal to W0, W1, W2, up to W sub D. Okay, and these are the weights that I came up with in the darkroom. Okay, and just to remind you, W0 is related to the threshold. W0 is equal to the negative of the threshold. Okay. Well, why don't I just forget about the fact that x0 is equal to 1 and incorporate that into x. So let me add a new component to x, which is x0. Okay. Okay. And the original x, so the original x was in R to the d. Okay. Now I'm taking this original x, which consisted of components 1 to d, and I'm adding x0 in here. So we're going to call this the augmented x. So this is the augmented x. And there's no harm done here. Basically what I'm assuming is that, whenever you collect your features of the applicant, just put in a 0th component at the top, which we're calling x0, and set it to 1. So it's always equal to 1. If it's the augmented x, whereas the original x was in r to the d, the augmented x has a component which is 1. So this is in the space which is 1 cross r to the d. So it's got a 1, and then the rest of it is in r to the d. This is one way of telling you that this augmented x always has a 1 in it. Okay? So from now on, for the rest of this course, unless otherwise specified, and we will, when we come to support vector machines, separate out the x0 component. But, for the moment, let us assume that whenever we talk about an input vector x, we will just assume that the augmented part has been put in. Okay, so it always starts with a 1, and then you put in the features. And why is that nice? That's nice because now the input vector x and the set of importance vectors w have the same dimension. Okay. So this is now in r to the d. This is also d-dimensional, but it's a special d-dimensional space. It's not the general d-dimensional space. The first component is always 1. Okay. So why is that convenient? Because with this representation of x and w, where the first component is always 1, this sum is exactly the inner product of x and w. So I can replace this sum with the inner product w transpose x. Okay. So it's just a little bit more convenient. Okay. I don't need to keep writing a sum. It turns out that convenience also translates into algorithms and so on and so forth. So it's more than just pure convenience. Okay. Now I want to emphasize that this is Malik's rule for approving credit. Okay. And we came up with it using a very natural process of constructing a credit score and comparing to a threshold. So now, we set up a framework for learning. Okay, so we set up a framework for learning in which, you have a target function, f, that produces a data set, dn. Okay. And the final output of the learning process is this g, okay, which is supposed to approximate f. Okay. And we said that whenever you produce a g that approximates f, then you have learned. Okay, so in this situation, we have produced a final hypothesis with Malik picking these weights, 10, -5, 1, and so on. Okay, and then a question arises, does g approximate the true target function? Okay. And the answer is probably not, but this is probably a reasonably good way to approve credit. Okay. Now, it's important to emphasize that g sub Malik is not equal to the target function f. Okay. And I'm going to mention at least 2 ways in which this is the case. Okay. So the first is that, Malik chose a set of importance weights to use in constructing the credit score and then comparing to a threshold which corresponds to taking the sign here. Okay. So Malik chose W. Okay. And they may not be the right weights. He made a mistake. Okay. And so may not be correct. Okay, that's not a big deal. Okay. Maybe we can change the weights. Okay. But there's a sort of more devilish way in which this can be the wrong credit approval formula, which is that the target function has nothing like this simple credit score based formula. Okay, so f does not have the same form as this nice simple compact approach. Okay. And we will find ways to deal with this also later. So basically what that amounts to is you need to choose better features. Okay. Or you need to choose a more complex form. Okay. But for the moment, it's just important to emphasize that, I came up with a formula. It may not be the true target function for these two reasons. But we will say that Malik has learned the right credit approval formula as long as it approximates the true target function. So as long as this is true. Now, this is the situation where we did not learn from the data. Malik didn't even use the data in coming up with this formula. But our machine learning setup, says that, you have a hypothesis set. Okay, and there's a learning algorithm. So to complete the setup, you have a learning algorithm. Okay, and it's the learning algorithm that produces the final hypothesis by picking one of your hypothesis set from one function from your hypothesis set, and typically you're going to use the data in order to do so. Okay. Whereas here we just came up with the credit rule. So let me show you that this credit rule can be put within this framework. Okay. And all I need to do is to show you that effectively Malik was the learning algorithm, and what Malik did was pick a specific final hypothesis from a particular hypothesis set. And what is the hypothesis set that Malik was effectively using? Even though Malik didn't do it that way, but effectively Malik was using all the hypotheses of this form. So let me define a hypothesis of this form as, h of x is equal to sine of w transpose x. Where now I will differentiate between the hypothesis that Malik formed and all the hypotheses of this form by saying that Malik picked a set of weights w star, because they're special. So I'm going to now emphasize the fact that these weights are special. They're Malik's weights corresponding to the 10, the -5, the 1, 0, etc., etc. But a generic hypothesis of this form could be represented as h of x equals sine of w transpose x. So a generic hypothesis of this form. And what is this? That form. Okay. And now that I've come down to this generic hypothesis of this form, we can consider all the possible weights w, okay, that can be used in here, and that defines a set of hypotheses. So let me define a set of hypotheses, a hypothesis set H, which is the hypothesis of the form h of x, where h of x is equal to the sine of w transpose x, and w is in r to the d. Okay, so you give me any set of weights you want that belong to r to the d, okay, and I can construct the corresponding hypothesis, and if you consider all possible weights that are in r to the d, I enumerate in some sense a set of hypotheses. Okay. Now, effectively, what Malik did was pick one hypothesis from this set. Okay. Which one did Malik pick? Malik picked the one corresponding to the weights w star. So this was Malik, the learning algorithm. Okay. And Malik was actually using this hypothesis set in here, picking one of these weights, okay, producing it as w star, and then saying, here, I've got my final hypothesis, G sub Malik. Okay. Now, in that case, he didn't learn from data. Okay. So, the role of learning in this setup is twofold. Well, the first is to replace Malik in that process. So one, we're going to replace Malik. Okay. So instead of Malik picking a hypothesis, an algorithm will pick the hypothesis. So instead of Malik picking, an algorithm will pick. And two, Malik just came up with those weights and we have to trust Malik. But no, the algorithm will use the data. And that's why it'll be an algorithm that learns from the data to produce a G that's approximately F. Algorithm will use the data. Okay, so now what have we accomplished? What we have shown is that a perfectly natural way of approving credit based on a credit score, okay, corresponds to the learning framework that we had before, the learning problem setup that we had before, with a very particular hypothesis set, okay, containing functions of this form, okay, and you know, if we can come up with a smart way to pick one of these hypotheses, okay, then we will produce a G, okay, and that's what Malik did. Okay. And we're going to now figure out how to do that without Malik, but replacing Malik with algorithm plus data. Okay. Now, what does our algorithm have to do? The algorithm has to pick, just like Malik did. Although Malik, it didn't appear that Malik was picking a hypothesis, he actually was. Okay. And in order for the algorithm to pick, as we discussed earlier, we need two things. We need a way to pick a criterion on the basis of which we will pick one. So in other words, we need a way of deciding, you know, which hypotheses in here are good and which are bad, and then we'll pick one of those. Okay. And once we have a criterion for picking, okay, we need to actually physically go and pick. Okay. And you know, in order to discuss both of those, I want to point out, okay, that Malik did something very sophisticated. And why? Because look, effectively he picked a hypothesis from this set, okay, which is uncountably infinite. So this is uncountably infinite. Infinite. So it's an uncountably infinite set. This hypothesis set is called the perceptron. And sometimes we will also refer to it as the linear model for classification. Okay, linear because it's linear in all kinds of things. It's linear in W. So this W transpose X is what's called a bilinear form. It's linear in W and it's linear in X. So when we say linear model, typically what we're referring to is the linear in W, but the linear in X is also important. And that's going to become clear when we discuss the geometry of the perceptron. That's what we're going to discuss next. Okay, so in order to figure out a way to choose, so in order to figure out the criterion on which to choose and an actual algorithm that does the choosing, you know, it's going to be helpful to sort of at least discuss a little bit the geometry of functions of this form. Okay, and so let's discuss that now. Okay, the geometry of the perceptron.